Okay, we need to talk a little bit about simple harmonic motion. We're still talking about this main idea of energy, which we've been talking about for a long time. So we're going to pull in some of those concepts of kinetic and potential energy and how they're being expressed, and the way they're being transferred, and look at some pendulums and introduce some vocabulary words like transverse and longitudinal. You'll remember from our thermodynamics unit that all particles are in motion because of their temperature. Whenever we're looking at a solid, the particle's movement does not have enough kinetic energy so that it can escape the attraction that it has to the other molecules around it. If the molecules move fast enough, they'll begin to get enough energy that they can break apart and be stronger than the forces that attract them. If the kinetic energy is so great that it starts breaking the bonds of attraction, they start flowing, we get a liquid. Whenever they move so fast, they completely separate and they can break those barriers entirely and start moving freely about their container. We call that a gas. It's important to remember that there is motion between these particles. They're bouncing around and moving. One of our best examples of simple harmonic motion would be a pendulum. A pendulum is an object that's attached at one point, and as it swings back and forth in a gravitational field, it's converting kinetic energy to potential energy and back and forth. If this is an environment that has no friction, it'll be able to repeat this over and over. We call it simple just because of how few factors are involved here in this motion. When we were ever looking at the motion of the particles, obviously that movement was much more complex. We're trying to take away as much as we can and look only at these few things to try to get an idea of the rules that are in place here. If we were to look at a spring bouncing back and forth, the pink object there is some mass, and it had to have been given an initial displacement. The x here refers to the displacement. Now, before the spring was compressed at all, that means squished together, before it was expanded, it would have been sitting at the 0 point. At the 0 point, there's no potential energy. In the graph off to the right, our potential energy is measured by the blue line U. The K, the pink line, is kinetic energy, and hopefully it's apparent to you at this point that no matter at what point, the red line, the total energy is remaining constant. We're just transferring back and forth from kinetic to potential. This is similar to what we saw back in previous units with like roller coaster physics. We're just looking at an oscillator at this point. Now what's important about the oscillation is that it moves back and forth around the central location, so that as we go left and right, we're moving back to the same area. This is similar to what we saw in circular motion, so we're getting things like periods again. The positive x and the minus x are going to be two extremes wherever we've converted as much as we can to potential energy. And if you imagine the situation, this should be clear, because if you were to stretch the spring to either of these locations, stretch or compress, and let it go, that potential would be released into movement. Now this means that at point 0, it had no potential energy, because if you left it there, that's where it was naturally sitting, it wouldn't be moving. Now in this case, because we've already given the spring some energy, point 0 is where we have the highest kinetic energy, because it's been pulling itself back to that point, and that's when it's pulled itself so hard it's going faster and faster. Now it's stopping pulling, so it's not going to speed up anymore, because it's not going to pull anymore once it gets to that point. The important thing to remember about it being a plus and a minus is after it pulls itself to the other side, it's going to start pulling it back and slowing it down, which is why the kinetic energy is being converted back to potential. If we go right back to our pendulum, we can see that our pendulum moves in such a way that at the bottom of it, that's like the 0 point on our spring. That's whenever it has the highest kinetic energy, right here in the middle at the bisector line. Whenever we get to the edges, it's gained more height. In this case is where the potential is coming from. This is a gravitational potential energy, not an elastic potential energy that we saw in the spring. Whenever it gets to those high points and it's storing that gravitational potential energy, it has 0 kinetic energy. For a moment, you can see it stops moving, and then the gravitational field pulls it back down. That gravitational potential energy is being converted back to kinetic energy. My pendulum follows very specific rules. You likely won't be expected to do these calculations, or at least not in a complicated manner. You'll have to be able to plug these in. What's important is to recognize what variables are in here. 2 pi is in there because remember I told you this is similar to circular motion, so we're going to use some of those 2 pi in there to do this calculation in a way that circles are done. The t is our period. You should recognize that as well. That's the time that it takes to complete one cycle. L would be the length of the pendulum, how long the string is. Now we make an approximation. We assume that our spring, or the length of the string adds no mass to the equation. And G is our gravitational field. Now, what's interesting is the things that are not in this equation. What's not in this equation is the amplitude, meaning it doesn't matter if the pendulum is pulled just a little back or if it's pulled all the way back. Amplitude does not fall into this. It will not change it. The other thing that will not change it is if we have a very small ball attached to our pendulum or a very large ball, the mass of the ball is irrelevant. The only thing that matters is how long is the pendulum, what's the length, where are we doing it, what's the gravity in that area, and that will determine what our period is. Only length and gravity. Nothing else on the pendulum will change it because nothing else is accounted for in that equation. Now we start moving from simple harmonic motion into a collection of these things. Many particles in a row moving, we'll call that a wave. Now there are 2 different kinds of waves. Let's start with the first, it's transverse. That's whenever we have the particles moving in a different direction than the energy moves. So let me just get a pulse moving here. So I kind of whip this rope real quick, and there my pulse moves. It's important to notice they put a couple green beads along the way. That way you could see that the only thing that was really traveling down that's actually making the big displacement is the energy. Energy moves, not mass. That's extremely important as an idea. So if you look at the particles, they do move up and down, but they return back to their same position. So I'm not saying they're staying still, I'm saying they're not traveling. The energy will move perpendicular at a right angle to this. If I put them going very fast one after another, it's a little bit easier to see the energy moving. If you just look really closely, there's an illusion that it looks like the particles move, but if you stare at just one green dot, you can see that it actually only moves up and down. And so that is our definition of a transverse wave. The particles aren't moving, the energy moving. And the energy is moving left and right while the particles move up and down. Now you could flip that as long as they're both moving in different directions at right angles, perpendicular. That's going to make this a transverse wave. My second one is called a longitudinal wave. Now in a longitudinal wave, the direction of energy and the direction that the particles vibrate are the same direction. Sometimes it's called a compression wave because they're kind of squeezing together and spreading apart. They're parallel. So if you just watch it, you can see a line of particles as if they're moving from left and right. But again, that's an illusion. That's energy that's moving. If you pick out just one particle, if you look at just one of them, you can see it's only vibrating left and right. Left and right. That is the direction of motion of that particle. It vibrates in simple harmonic motion about that one point. But if we look at all the particles together and we see this wave, we can see that the transfer of energy throughout the wave is moving to the right. So there is a transfer of energy, but the particles are only moving about their spot. What makes this a longitudinal wave is that direction of vibration and the direction of energy transfer are the same. That is the only thing that separates my longitudinal and my transverse wave is the direction of energy versus the direction of vibration. So the important ideas that we discussed here, just in our brief introduction here to harmonic motion, is the idea that kinetic and potential energy are still being transferred back and forth in pendulums and in springs. At their 0 point in the middle, that's when they'll have the greatest kinetic energy if they're in motion. And as they get to their extremes, the further they are away from equilibrium, that's when they have the most potential energy. They're only transferring energy whenever we're moving in a wave type situation, not mass. The things that affect pendulums is length, gravitational field, and the period. What's important is that the mass and the amplitude do not affect the motion of our pendulum. And lastly, the direction in transverse and longitudinal waves. In a transverse wave, that's where our particles are moving perpendicular to our energy. Our molecules vibrate one way, but our energy moves in a different direction. In a longitudinal wave, the two are moving together in the same direction. That is the basics of simple harmonic motion.